All right, I make it a couple of minutes after 4 o'clock, and I see that all of award winners have joined, and the number of people still joining seems to be slowing down. So in that case, I guess we should get started. So my name is Colin Perkins from the University of Glasgow. I'm the IRTF chair, and this is the IRTF open meeting for IETF 112. So I want to start with the usual note well and reminder of the intellectual property rules for the IRTF. The IRTF follows the same sorts of intellectual property disclosure rules as the IETF. You know, if you're aware of contributions, if you're aware of patents or patent applications that cover the contributions. That you make that are controlled by you or your sponsor, you do need to disclose that or not participate in the discussion. Perhaps a difference from the IETF disclosure rules is that the IRTF expects you to file these disclosures in a timely manner in a period of days or weeks rather than months. And we expect the most liberal licensing terms possible are made available for IRTF stream documents. And if you need more details about this process, the RFC is listed on the slide. RFCs 5743, 5378, and 8179 give details of this. And the URL irtf.org/policies/IPR also has links to these and more details on the process. Also, as should perhaps not be a surprise, the IRTF makes recordings of online and in-person meetings, and this includes audio, video, and photographs, and so on. This session is being streamed live. I believe we're going out on YouTube, as well as being the Meet Echo session, and as well as being recorded, and the recording will be on YouTube after the session as well. If you participate online, if you turn on your camera and microphone and make comments at the microphone, then you are considered in the recordings. And I'd also remind you that the chat logs in all of these Meet Echo sessions are recorded and are available on the IETF site. So what you put into the chat is also recorded. I'd also like to remind you that we have a code of conduct in the IRTF and in the IETF. And you know, as a participant, as an attendee at the IRTF sessions, you agree to work respectfully with the other participants in the session. You agree to behave in a professional, respectful, and polite manner. And you know, we have the code of conduct, we have the anti-harassment procedures, which you see linked from the slide that go into a lot more detail about what we mean on that. If you have any concerns about behavior of the various participants, the Ombuds team, again linked from the slide, is available to sort of investigate those and to act as a point of contact if you have any issues with the participants in the session. If you provide any personal data, and in order to register, you would have had to provide at least a little bit of personal data, that's handled in accordance with the IETF's privacy policy, and again, that's linked from the slide. So what are the goals of the IRTF? Well, the IRTF is there to provide a forum for longer-term research issues, while the parallel organization, the IETF, focuses on shorter-term issues relating to engineering and making standards. The goal of the IETF is very much to conduct research. We're not a standards development organization. And while the IRTF research groups can publish informational or experimental documents in the RFC series, the primary goal of the research groups is not publishing RFCs, it's not publishing documents. is to promote collaborations, it's to promote research, it's to promote development of research ideas that relate to the internet protocols, applications, architectures, and technologies. We have a very nice RFC that Spencer Dawkins wrote a few years ago, RFC 7418, which gives an IRTF primer for IETF participants, which talks about some of the differences between the goals of the IRTF and the IETF. So if you're not familiar with that, I would very much encourage you to have a look at that. The IRTF is arranged as a set of research groups. We have 5 research groups, which are highlighted in dark blue on this slide, which are still to meet later this week. The Crypto Forum research group develops cryptographic algorithms and looks for an understanding of various cryptographic algorithms and techniques, and many of those are used in IETF standards. The computation in the network group is looking at all aspects of in-network computation, programmable networks, and the impact of programmable forwarding hardware, programmable control planes on the internet architecture. The path-aware networking group is looking at the interplay between the endpoints and path elements and how that communication should happen. The privacy enhancements and assessments group, which my apologies to the chairs, I noticed this was listed as still a proposed group rather than a full group in the plenary slides, is looking at privacy enhancing technologies. And the human rights protocol considerations group is looking at the impact of standards on human rights and the way we can reflect various principles from human rights into the types of protocols we develop in the community. We also have a number of groups which have either met or either met already or are not meeting at this session, including the MapRG, which had a bunch of interesting measurement papers looking at the network architecture in the previous session, and the network management, global access, and congestion control groups, which met yesterday. The research groups in the IRTF require some understanding of the various research questions and problems that are interesting in a particular area, and are looking into understanding the relevance of those problems and questions to the internet. They're built around a particular community which is trying to conduct relevant research and that has been interested in bringing that research to the IRTF. And they're built on an understanding that there is a benefit for conducting that work in the IRTF, both for that community that brought the work in and for the IRTF and the broader internet community. The goal of these groups is very much to understand a problem, right? That they're not there to lend support to particular outcomes. They're not there to produce documents in the way that IETF groups are. The goal is understanding rather than products, rather than RFCs in the IRTF groups. That said, the groups can publish RFCs. We have had one RFC published on the IRTF stream since the last meeting, which is RFC 9106 on the Argon2 memory hard function for password hashing, which came out of the Crypto Forum group. But as I said a minute ago, the main focus is on developing understanding, and in the vast majority of the research groups, I think research papers and discussion and understanding is a much more common output than the RFCs. So that's what I wanted to say about the IRTF. There's a couple of other activities been happening, which I want to mention in this introductory talk. The first is that the Internet Architecture Board has a program running to develop a new model for the RFC editor function. And this program was created after the departure of the previous RFC series editor, I guess a year, 18 months or so ago. I forget the exact timing. Back in the times when we all used to meet in person in windowless hotel rooms, so that, I guess it was a while ago. And that program has been developing a new model for how the RFC editor function is organized and arranged. The model they're proposing has some fairly significant changes to the RFC editor function. It's proposing to change the RFC editor role to that of a consulting editor, which will be known as the RFC series consulting editor, who will be an expert that will provide guidance to the community, to the RFC publishing streams, and to the RFC Publication Center. And it's proposing to shift the responsibility for oversight of the evolution of the RFC series from the Internet Architecture Board to a new working group, which will be known as the RFC series working group, which will be a working group which is independent of the IETF and the IRTF and the independent stream, and will just act as an oversight for the series. And once that group reaches consensus on proposed changes to the operation of the RFC series, there'll be the proposals will then be reviewed by an RFC series approval board, which will comprise the RFC series consulting editor and representatives of the various streams, which are likely to be the IRTF chair, the IETF chair, and the IAB chair, although they can delegate that if they need to. But it's shifting the responsibility of the management of the RFC series from the IAB onto the community. Now, this may seem like a fairly, a bit of a process arcana, but it's actually a fairly significant change to the administration of the RFC series going forward, and potentially has the ability to impact the way the IRTF can publish documents, since if the way the RFC series changes, the way the IRTF may use it changes. The new model, the description of this process is described in an internet draft that the IAB have published, that this program have published, draft IAB RFC Ed future RFC Ed model, if I got the draft name right. That's just completed a last call in the IAB program and is about to enter a community-wide last call for comments. So I would encourage you as participants in the IRTF to review this document and provide feedback to the RFC editor future development program. They have a meeting tomorrow in the 14:30 UTC slot. They also have a mailing list by which you can provide comments. And as I say, please do review this document. Please do send feedback on whether you think what's being proposed is or is not appropriate, as you see fit. All right, on to perhaps happier notes than the arcana of the IETF and IRTF process. The next thing on my list today is to congratulate one of our research group chairs, Vincent Rucker. And I believe Marie-José has something to say on this topic. Marie-José, are you there? Go ahead.
You hear me? Yes. Okay.
Yes.
So somebody has echo. This morning, actually, it's a new thing. This morning at 11 a.m. Paris time, Vincent received his award. He's now a Chevalier of the Ordre du Mérite of scientific work of the French government. And while the award was given to him for this contact tracing system or protocol that they put together for the French government, it was actually highly mentioned in the presentation from the French government official that Vincent was a major contributor to the IETF with 14 RFCs, which I think is I think there's 2 French people who have tons of RFCs, the other one being Christian Utema of the IAB. And so that was actually mentioned as a major contribution. Also his work in the IRTF, which I am very much aware of. But what was mentioned was also, I think, what we all came to appreciate of him, the hard work, the community spirit, the fact that he's always open to new ideas, a very team leader, very committed to the people he works with, also to his family and to the environment. It was funny for those of you who know him that he had a shirt and tie and a jacket, which is like a first for me. But I think it was highly, it was highly deserved. And I think we always forget that there are people like Vincent who are not like the most vocal and who are a little bit quiet, but in the end do all the major work. And I felt this was such a great recognition of all his achievements. And I'm absolutely proud of having been his co-chair. Thank you.
Yeah, thank you, Marie-José. Congratulations to Vincent. As you say, this is an incredibly well-deserved award. Vincent has been involved in the IETF and the IRTF for very many years and has made some really tremendous, some really important contributions. So I think that this is astoundingly good news. All right, continuing the good news. One of the more pleasurable parts of being the IRTF chair is that we get to award the Applied Networking Research Prizes, which we organize in conjunction with the Internet Society and with support by Comcast and NBC Universal. These prizes are awarded for some of the best recent results in applied networking, for some interesting new research ideas which may potentially be relevant to the internet standards community, to the internet research community, and to recognize upcoming people that are likely to have an impact on internet standards and technologies in the future. And in normal times, we would bring these people to an IETF, an IRTF meeting, and I would be introducing them to you in person, and we could chat with them in the breaks and bring them to the related sessions. Of course, in these times, that this is not necessarily possible, but I hope they will be around for the week and in some of the breaks, and you can chat with them, and we can try to get some interaction going. But it's my pleasure to announce that the winners of the Applied Networking Research Prizes, which are being presented at this IETF meeting, this IRTF open meeting, are Thomas Wertgen for his work on extensibility of Bgp implementations and other routing protocols. They have to Axa Kashaf for her work looking at third-party service dependencies on the internet. And they go to Kevin Bock for his work on internet censorship and the evasion of various censorship techniques. So congratulations very much to these 3 speakers. We will see the talks in a few minutes. If you do see these people around, and I see they're in the chat here, but if you see them around at the rest of the IETF sessions or during the breaks, please do talk to them, please do congratulate them. I think this is some really nice work we've got here. And in addition to that, the nominations for the 2022 Applied Networking Research Prize are now open. The deadline for these nominations is the 19th of November, so you have 10 days. So if you know any interesting applied networking research, if you know any good papers in this area, if you know any people who you think will make interesting contributions to the community, any work which you think is especially valuable and isn't getting the recognition it deserves, then please go to the website there. please make the nominations. And we very much encourage both third-party nominations, where with someone's permission you nominate someone for the prize, but also self-nominations. If you think your work is deserving of the prize and isn't getting the recognition as it deserves, then please do nominate yourself. And if you're shy about that, reach out to me, and I will happily discuss this and highlight whether I think you should be nominating the work, and be as encouraging as I can to get as much work in as we can. And for the community, if you have, as I say, if you're aware of work which deserves the prize, please do nominate. And with that, we'll move on to the talks. We have 3 talks, and we're running a little late, but I think not all of the talks use their full time. So the first talk is by Thomas, talking about XBGP, and in a certain amount of irony, that the talk entitled "When You Can't Wait for the IETF" is presented in the last of the 3 award talks of the year. So I guess there's something to be said there. The last of the 3 IETF meetings where the award talks are presented in the year. Axa's talk on analyzing third-party service dependencies will follow that in about 30 minutes. And then finally, we'll have Kevin talking about censorship and server-side censorship evasion. So with that, I'm done. We will move on to the first of the pre-recorded videos, which is by Thomas Vertgen. My apologies if I'm mispronouncing the name. Thomas received his master's degree in computer science from Louvain in Belgium in 2018, and started a PhD looking at the extensibility of routing protocols under the supervision of Olivier Bonaventure. He's currently working on techniques to improve the programmability of BGP, which led to the prototype XBGP system that he'll be talking about in this talk. And his research interests include distributed routing protocols, programmable networks, and system architectures. He'll be talking about the paper XBGP, When You Can't Wait for the IETF and the Vendors, which was originally presented in the ACM HotNet Symposium in 2020. And I think Thomas is in the chat, so if there are any questions for clarification, any quick questions during the talk, we can ask them in the chat, and then he'll be available to answer questions live after the talk. So thank you, and Meet Echo, if we can play the first of the videos.
Hello everyone, my name is Thomas and I will explain you XBGP, a new way to add flexibility inside a routing protocol. So why it is needed to bring programmability to a routing protocol? Imagine yourself as being a maintainer of an autonomous system. The current best practice today is to have routers from different vendors. But the problem is that you don't have a unified interface to configure your routers. And the second problem is that if you would like to add a new functionality inside your network, then all the routers must implement the functionality. But all of the routers do not implement the same set of functionality, and this is a problem. And the other problem is that if you would like to add a new functionality which is not standardized or implemented to the routers, then you need to pass to a standardization step by the IETF. In average for BGP, it took 3.5 years. On the slide, you can see the standardization delay of all BGP features. So we measure the time since it is released as a draft to the moment it is released as an RFC. This is not an isolated case. Other routing protocols suffer from the same delay, but studies have shown that this is also the case for other RFCs. Next, you need to implement your feature to the operating system vendors, and finally, the routers must be updated. But if you are a small network such as Belnet, you cannot easily influence step 1 and step 2 because you don't have enough impact to actually convince routers vendors and the IETF from your new feature. Because of those problems, we introduce XBGP that is designed to bring back innovation to the network operator. We would like to open the BGP box so that the network operator can actually modify the protocol. I will explain you how XBGP works in practice. We start from BGP, which is considered as a black box. You can configure BGP with multiple interfaces, for example, CLI, netconf, or SNMP to make some monitoring. So those are the main interfaces to configure. But you don't have any way to modify the protocol, you as being a network operator. XBGP will open the lid and will expose the protocol and the protocol memory. Inside the protocol, you can add a new state, you can modify existing state, and also you can modify the transition between two states. Concerning the protocol memory, you can access to the routing table, you can also access to other internal data structure. Now, the operator, thanks to the interface of XBGP, can now add extension code to their router. So they write the extension code once, it will compile to a bytecode, and this bytecode will be executed to all the routers which are XBGP compatible. Now, actually, XBGP is added on the top of operating system vendors. Now, the routers can be seen as a kernel where you can actually run some extension, which is the modification to your BGP protocol. Now, I will explain you how XBGP works inside BGP. But before, I will take an example of a new feature which is not standardized by the IETF and not implemented inside any operating system. So what we would like is to add the geographical localization of the router who receive the BGP update to make some, for example, filtering or some analysis. This information about the geographical localization will be added to the BGP update that will be spread to other routers of your network, and so that other routers can use your functionality that you have implemented. And then, in order to not spoil the other neighbor, you will remove your geographical localization from the BGP update. If you would like to add this new feature inside the BGP protocol, then you need to think about how BGP implementation works. Normally, all the BGP implementation follows the RFC 4271, and inside the RFC 4271, it explains the BGP workflow. First, you have BGP message that come from your peers. It will pass to the Edge ribbon. Then inside the import filter, when it passes the import filter, it goes to the local RIP. All the acceptable routes inside the local RIP will be taken to the BGP process to take only one base route that will be pushed to the forwarding table of the routers, and then putting inside the export filter to check whether or not the route can be exported to other neighbors. And if it is the case, it will be stored to the Edge rebound, and finally, the message will be generated. If I take back my geographical localization extension, you need to modify multiple steps of the BGP protocol, and those are represented by the blue arrows. With BGP, it is possible to modify the protocol thanks to the introduction of insertion points. Insertion points are a way to execute arbitrary code. And so if I take back my geographical localization, it is composed of multiple subparts, and those subparts will be added to the right insertion point. But that's not all, because our extension must talk to the protocol memory to retrieve the geographical localization. And this is done via the XBGP API. And this is something that makes the interaction between the plugin and the protocol memory. Now I will explain you the XBGP API. This is a way to communicate with the BGP implementation. And all the extension code or plugin must use this API to retrieve or set some protocol memory. Why? First, because it ensures isolation of the plugin and the BGP implementation. And second, it is a unified way to access to the memory. Remember that XBGP must support multiple BGP implementation. The XBGP API contains multiple functions, such as function to send and read BGP messages, also the function to get or set some memory inside the protocol memory. For example, for the geographical localization, you must access to the geographical localization of the router. Then you use a getter function. You have also function to access to the routing table and other utility function to manipulate the memory or doing simple math function. So now we have the big picture of XBGP, and I will show you some use case that you can do with XBGP. But before, you need to adapt some Bgp implementation to make them XBGP compliant. We have FRouting and bird in our case. In the slide, I've put an array with all the line of code that you need to modify or add to make the Bgp implementation XBGP compatible. The first use case is a simple one. This is the monitoring. And what we would like to do is to monitor the length of the AS path. Actually, it is difficult to achieve it with traditional interface, but with BGP, you have an interface that is easier. Why we would like to monitor the AS path? For example, you would like to monitor it to filter out large AS paths or make analysis afterwards. So now I will explain you a complete example of C code that represents the XBGP expansion. First, you need to retrieve the data from the host implementation. This is done through getArg function. So this is a function of the API. Then you will do your computation. So here you will parse the AS path attribute and count the number of autonomous systems contained inside the path. And then you will use another function to actually log the number of AS you computed. This extension code will be added to the import filters. The second use case is related to the use of BGP inside data center. In data center, you use BGP to make your internal routing. All the best practice concerning the use of BGP in a data center is stated in RFC 7938. Inside this document, there is a constraint. You don't have any zigzag path. So for example, to go from level 2 to level 0, you must go to level 1 and level 0. But you cannot make some zigzag path between level 2 and level 1, for example. And to avoid this zigzag path, you must have the same autonomous system number for all routers of the same level. So here, level 0, all routers have the AS1 number. But these constraints make debugging difficult. If you would like to check where the routes are sourced from, you cannot, because all the paths have the same autonomous system for the same level. And so you cannot decide if the packet goes through the left part of the data center or the right part. But now, with XBGP, you can get rid of this constraint and put a different autonomous system number for the routers of the same level. To do so, you must first design your XBGP extension and pass them a data center topology configuration, so that you can actually check if there is any zigzag path to your data center. This extension will also be put on the insertion point related to the import filters. The third use case is related to the route selection. So in this slide, we consider a stub network, so the source network connected to several transits, transit 1 and transit 2, and to reach the network destination, BGP must advertise a route to the source. The source will directly receive the green route via transit 1 and another one from transit 2. According to the local transit 2 policy, it will either announce the blue or the yellow path. Maybe transit 2 choose the path for its security properties, but the source prefers a path with a lower latencies. And so the ranking of the source and the transit does not match. XBGP can solve the problem to execute a plugin that will choose the route on the edge router of transit 2 according to the source ranking network. And so transit 2 choose the route the source prefers. This path selection service will be added to the decision process insertion point. The last use case is about detecting BGP zombies. If you know a prefix P, then your router will announce that it can reach the prefix P, and the other router will do the same by advertising to the neighbor the prefix P. And so all the routers can reach P. But now consider prefix P is no longer reachable. So the routers will send a withdraw to the neighbor, but for whatever reason, due to a software bug or misconfiguration, the router cannot process the withdraw. And so it fails to send a withdraw to the other neighbor. The upstream router will still have the P prefix in their forwarding table. This is something we don't want because it may lead to some blackholing of traffic. And this is a BGP zombie. This is a route that is still in the feed of some routers, but no longer reachable anymore. With XBGP, you can actually detect those BGP zombie routes. you need to write a plugin that will analyze the routing table and flag all the routes that are older than a given threshold. Then, for all those prefixes, it will ask to the upstream router to confirm if the route is still valid or not. There are some mechanisms in Bgp, such as graceful restart, that can actually reload all the entire routing table of the neighbor. But since Bgp Zombie is concerning a small fraction of prefixes, according to some measurement inside the internet, it is not really necessary to reload all the entire routing table. So we designed a prototype that only asks for those Bgp zombies that we detected. This extension code will be added to the background task insertion pod, which acts like a cron job. So each unit of time, you will re-execute this plugin. So now we've seen some use case that we can do with Bgp, but the code that is executed is untrusted, and we can ask the following question: could it break XBGP? Well, we need to have an automated way to verify some properties before injecting it to the routers. With XBGP, we make the following approach. First, you start from the extension source code that you will annotate. Then it will be passed to the software verification tools. And if the verification tool says, okay, the code can be trusted, it will be compiled to the bytecode and then injected to the protocol. Now I will explain you some properties that we define that all the plugin must satisfy before being injected to the routers. The first one is the termination properties. We do not want that an infinite loop, for example, breaks the protocol. Another property is related to the memory isolation of the plugin. All plugins must not modify memory that are not authorized to modify. We also restrict some API functions to some extension code. For example, for the monitoring, they do not have the right to modify the protocol. Finally, we use CRD, another verification tool, to verify properties related to the BGP syntax. As an example, we will verify the syntax of the geographic coordinate extension. So this geographic coordinate extension is defined on a draft, and it must follow the format specified on this draft. And those properties I've defined on the slide are those that must be followed by the plugin. We write all the properties and we annotate the plugin, and then this annotated plugin will be passed to the verification tool solver that will say yes or no. And if it says yes, then we are the guarantee that all execution of the plugin will satisfy the constraint. To conclude, with XBGP, you can make Hvp implementation truly extensible. If you want more detail, you can read the paper related to this presentation. We have also a website that collects all the source code of XBGP. We designed a methodology for BGP, but the methodology could be also applied to other routing protocols. Thank you.
Okay, thank you. Really interesting talk. Thomas, if you're there, you can open up your video.
Hello.
We have some questions. Hi. Okay. Can you all hear us? Yeah.
Yes, I can hear.
Okay. Well, yeah, as I say, really interesting talk. Do we have any questions for Thomas? I see Elliot had something in the chat. Elliot, do you want to maybe go ahead?
Yeah, thanks very much for your talk. It was very interesting. 2 points. The first is a question. Is in terms of that last slide, it was your desire for this mechanism to always have the transitive bit set to 0, which I think does allow for a certain amount of prototyping, for instance, right?
Yeah. This is actually Xbgp is designed for quick prototyping. We just add an interface to allow some network operators to implement quickly its functionality, and then it will actually test in another network, and finally it will be maybe if it works well in maybe released on the production routing network. But actually, if you would like to have performance, you have to write it directly inside the implementation code. So yeah, maybe when you introduce new code, you will actually break some rules of the BGP protocol, but we designed some mechanism to guarantee the execution of the plugin locally. But the execution in the global network is not something we've done, and this is something that you can you test on yourself. So you make some tests, and if you are confident about that, you will push on the network. So there is no really a way to test the global safeties of the implementation you put on the router. So maybe this is something we can actually do afterwards, but I think this is something quite complicated to verify and satisfy the security property of the global network. But with BGP, we have also some just local verification.
Yeah, thank you. The reason I asked the question, obviously, is one of the reasons it takes 3.5 years to go through the standardization process is because I think people are routing is a difficult business to begin with, and we do see cases where routes disappear for sometimes inexplicable reasons, even with the current mature mechanisms. And so there is a certain amount of proof time. And so one question I think one research question to ask is just how flexible should a routing paradigm be, and what are the guardrails that make it safe to experiment?
Hi, this is an interesting question, because with XBGP you can do pretty much what you can do. Well, the first thing is that you have to choose the right tool to actually guarantee the security property of the router. Maybe, well, now we write all the plugin in C code. This is not something which is really secure, but in another, we can also use other tools, maybe some language that are safer, like Rust, and those tools will be actually provide a better security. But yeah, we don't have any. Yes, maybe obviously there is a balance between flexibility and security. And if you add flexibility inside the routing protocol, then the security part will be less be part of the reasoning of the thing.
Yeah, thank you. So I sort of had a follow-on to that to some extent. I mean, if I understand right, this adds a bunch of hooks throughout the BGP implementation where you can insert different sets of functionality. How much of the core protocol has to be implemented in the core, and how much can be implemented in these programmable hooks? How much of the core BGP logic is hard-coded, and how much is extensible?
Actually, what you have to do to put XBGP inside an implementation is to first follow the original RFC, so 4271, and we also need all the extension above multi-protocol. For example, in the paper, we reproduce the root reflector functionalities, and this is one of some use case that prove that we can actually implement a lot of complex thing. But the strong basis of XBGP relies on the original draft and multi-protocol extension. The other thing you can do, you can actually put your code inside the extension code and then put it in the implementation, which is XBGP compatible. But if, for example, if you want to modify some data structure which is hard-coded inside the implementation, you cannot. For example, if you take the functionality that enlarge the buffer of BGP message, so 4K to 74 kilobytes of memory to one message. This is one example of a feature that you cannot do with BGP. So everything related to the memory or internal data structure, which is really put it inside the implementation.
Oh, okay, that makes sense. That makes sense. Does anyone else have questions? If you put yourself in the queue, if you have. Elliot, are you still in the queue, or is that just left over from before? Okay, so I just had one last thing. I mean, obviously the focus of the mechanism is extensibility of the protocols, and you make the point of when you can't wait for the IETF, and I think it's well known that the IETF process takes time, and obviously Elliot mentioned some of the reasons for that a minute ago. And assuming we can't make the IETF go any faster, are there things you think we should be doing differently in the way we structure the protocols that will help this sort of experimentation once the RFC has been published? Are there any general lessons that can be learned from this, or is this very specific to the details of how BGP was implemented?
Actually, when we look at XBGP, the protocol was pretty well established. So if what we try to do with XBGP is to understand what are the properties of the protocol, and then we establish a set of properties to actually model a general architecture of the routing protocol. And then when you have the general model of this routing protocol, then you will look inside your implementation if it actually implements this kind of general model. And if it implement this general model, then you will be able to actually put XBGP inside the protocol. But yeah, if the implementation is really exotic, I would say, then XBGP will be more, it will be difficult to integrate inside the implementation.
Yeah, that makes sense. So I guess the general conclusion is that modularity in the way the specifications are written might make this process easier for developing modular APIs and extensions. Yeah, okay. So that's maybe something for the standards groups to think about. All right, and this is we're over time, and I don't see anyone else in the queue. So thank you very much. I think that's a really interesting talk, some really nice answers to the questions. If there are any more questions to Thomas, please put them in the chat, and maybe he'll be able to be around in the break afterwards if people want to catch up with him in the Gather space, perhaps, or of course drop him an email. All right, so thank you, Thomas. And we'll move on to the next talk of the session, which is by Aksa Kashaf. Aksa is a PhD student at Carnegie Mellon University. She's co-advised by Eva Seka and Yuvraj Agarwal, and I apologize, I must have mangled those names. Access focuses on network security, particularly distributed denial of service attacks, and currently she's working on building reconnaissance techniques to profile the capabilities of DDoS defense systems, looking at understanding and improving the resilience of the internet against DDoS attacks. The award paper today is analyzing third-party service dependencies in modern web services. What have we learned from the Mirai DIN incident? And it was originally presented at the ACM Internet Measurement Conference in 2020. So if we can play the next video, please.
Hi, this is Aksa. I'm a PhD student at CMU, and I'm going to present my work on analyzing third-party dependencies in modern web services. This is a collaborative work with my advisors, Vyas Sekar and Yuvraj Agarwal. The study is motivated by a DDoS attack that happened in 2016 on a DNS provider named Dyn. There are a lot of lessons to be learned from this attack, particularly its root cause. And as I show in this talk, we can expect more Dyn-like attacks in the future. During this attack in 2016, a lot of popular websites such as GitHub, Spotify, and Twitter were inaccessible to users for many hours. Here is an outage map of the attack. In total, 178,000 domains went offline and tens of millions of users were affected. The list of websites that went down goes on. It includes almost all the popular services we know. So how were the attackers able to bring all of these down? This was possible because all these websites, such as Netflix, exclusively relied on Dyn, a third-party DNS provider that acted as their authoritative name server. As a result, when the authoritative name server was down, a lot of websites were inaccessible to millions of users. Attacks like these raise many questions about the resilience of the internet. How easy is it to bring down the internet? Particularly, we need to understand how prevalent these kind of third-party dependencies are. For example, how many other websites are at risk of Dyn-like attacks? Are there other hidden dependencies that we also need to know about? There might be inter-service dependencies, which indirectly affect a website. And finally, since Dyn attack had such a huge impact, it is natural to think that websites would adapt as a result. How has the world changed in using third-party services as a consequence of the Dyn attack? For example, did websites stop using Dyn, or did they start using multiple providers? To answer these questions, we analyzed top 100,000 websites, Alexa websites. Alexa is an external service that ranks websites by popularity. Alexa rank is calculated from a combination of daily visitors and page views on a website. To see how the world changed in response to the Dyn attack, we look at the dependencies of top 100,000 websites in 2016 and 2020. In this talk, I'll first describe our measurement methodology to measure the third-party dependencies of websites, and then explain our main findings. Then, after the findings, I will also present some recommendations in light of our findings, and finally, some limitations of our work. To start with the measurement methodology, we first need to identify the services which are crucial for a user's access to the website. To do this, we look at the life cycle of a web request. When a user makes a request to a website, it first goes to the authoritative DNS server, which provides the IP resolution of the website. After the IP resolution of the website, user starts a TCP handshake followed by an SSL handshake if the website supports HTTPS. If yes, then the website provides a certificate which is verified for revocation by the user by contacting the OCSP server or CRL distribution points set up by the certifying authority. Finally, if the certificate is valid, the user requests the content of the website page. If the website is using a CDN, then CDN will serve this content. Based on this, we identify 3 services. The first one is DNS, second one is certificate validation by certificate authority, and the third one is CDN. Note that these by no means are the only services that a web request encounters, but we just identify these 3 services and define the scope of our work. Given these services and websites, we need to identify what exactly we want to measure. So we are interested in third-party dependency of a website. For example, here, the website TechRadar uses another entity, Let's Encrypt, as its certificate authority. Next, there might be indirect dependencies between websites and service providers. For example, here, Let's Encrypt uses Cloudflare as its authoritative name server, and hence TechRadar has an indirect dependency on Cloudflare. We are also interested in critical dependencies which exist if a service provider is integral for a given service. For example, here, if Cloudflare is down, OCSP servers of Let's Encrypt will not be accessible. Hence, Let's Encrypt has a critical dependency on Cloudflare. In case of DNS and CDN, we compute critical dependency by measuring if the website is redundantly provisioned, which means that the website is using multiple DNS or CDN providers. And in case of certificate authorities, we compute it by measuring if the website has enabled OCSP stapling. Here, TechRadar does not support OCSP stapling, and hence TechRadar has a critical dependency on Let's Encrypt as well as Cloudflare. If OCSP stapling is enabled, the user doesn't have to contact the OCSP server for certificate validation. So Let's Encrypt will not be contacted here. But if OCSP stapling is not enabled, then users of TechRadar will have to contact the Let's Encrypt OCSP servers to validate the certificate. Now, given this, we first describe our measurement methodology for DNS. What we essentially want is to find the authoritative name server of each website. This can easily be done by looking at the name server's resource record of a website. Then we want to identify if this name server is private or a third party. I would go into details for this in the next slide, that how do we actually identify if it's a private or a third party. And finally, for a website and its name server, we want to identify which of these name servers belong to the same entity. For instance, here, Azure DNS and O365 filtering both belong to Microsoft. So since live.com is using these two which belong to the same entity, it is actually not redundantly provisioned. To identify third-party name servers, prior work looks at second level and top level domains of the name server and the website. If they match, then the name server is private, otherwise third party. For example, here in case of Google, its name server also has the same second and top level domain, google.com. Hence, it gets correctly classified as private. However, this fails in case of YouTube, where the name server gets classified as third party when in fact it is not. Other approaches look at the start of authority DNS records, which contain administrative information about the DNS zone. If the start of authority record of the website and the name server are the same, then it's private, otherwise third party. This works in case of YouTube, but it fails, for instance, in case of Twitter, where it is using a third party name server, and its start of authority is also that third party. For instance, here Twitter is using Dynec.net, which actually belongs to Dyn. To cope with these issues, we add a few more heuristics. So for all website and name server pairs, we classify the name server as private if the second level domain and top level domain match for the website and the name server, or if the name server is present in the subject alternate name list of that website. SAN list is present on the HTTPS certificate of a website, which tells that this certificate will also work for the domains present in the SAN list. Hence, it's a good way to know if a given domain is private or not. If the start of authority do not match, we classify it as third. And finally, if the name server serves more than 50 websites, then we say that it's more likely third party. In general, we identify approximately 10,000 third-party DNS providers in our data. For measuring CDNs, we fetch the web page of the website that we want to measure the CDN of, and then we extract all the resources in the web page and identify the resources which are internal. For example, for reddit.com, this resource that comes from redditmedia.com is an internal resource. We use TLD matching, start of authority, and subject alternate named lists here as well to identify internal and external resources. We do this because internal resources, if they come from a CDN, then it means that the website is actually using a CDN. For all the internal resources, we fetch their CNAME records. If the website is using a CDN, then these CNAMEs will point to the CDN. For instance, here, the CNAME actually points to Fastly. We input this CNAME to our CNAME to CDN map, which will output Fastly here. We manually build this map by taking help from available CNAMEs on the internet, on the CDN's websites, and also in public suffix lists. After we have identified the CDN being used by a website, we also need to see if the CDN is private or a third party. And to do that, we again use TLD, start of authority, and SANS list to see if the CDN is private or third party. In general, we identify a total 86 third-party CDNs in our data. For certificate authority dependency, we just fetch the certificate of a website, and from that extract the links for the OCSP servers and the CRL distribution points. And we use the same techniques, which are TLD matching, start of authority, non-matching, and SAN list to identify if these are third-party certificate authorities or not. In our data, we identify a total of 59 third-party certificate authorities. Now we present our main findings. I will start by answering the question, how prevalent third-party dependencies are and how concentrated different third-party providers are. Overall, we find that 89% of the top 100,000 websites use third-party DNS, 32% use a third-party CDN, and 76.8% use a third-party certificate authority. Moreover, 85% critically depend on a third-party DNS provider, 28% critically depend on a CDN provider, and 59.5% critically depend on a certificate authority. For DNS and CDN, it means that they're using just a single DNS or CDN provider, and for CA, it means that they do not support OCSP stapling. All in all, we found that 89% of the top 100,000 websites critically depend on a DNS, CDN, or CA provider. In addition to this, we also found that critical dependencies are higher for less popular websites. For example, we observed that 49% use a third-party DNS provider in the top 100 websites and 89% in the top 1,000 websites. Same is the case for critical dependencies. For instance, 27.9% critically depend in the top 100, while 84.8% in the top 100,000. This means that more popular websites care more about availability. Now, since third-party dependencies are very prevalent, it raises the question of how concentrated various providers are. The greater the concentration, greater will be the single points of failure. This is a dependency graph of website to DNS dependency, where each edge shows the dependency of a website on a third-party DNS provider. The size of each node here is proportional to its n degree, which in the case of DNS provider is the number of websites using it. We observe that the topmost DNS provider, Cloudflare, alone serves 23% of the top 100,000 websites. In general, we observe that only top 3 serve almost 40% of the websites, when the total DNS providers we observe are almost 10,000. This indicates the DNS space is highly concentrated. We see similar trends in CDN, where the topmost CDN provider, Amazon CloudFront, alone serves 26% of the websites that use CDN. Particularly, we observe that only 3 CDNs serve almost 60% of the websites that use CDN, which are CloudFront, Akamai, and Cloudflare. The situation for certificate validation is also similar. DigiCert alone serves 28% of the websites that support HTTPS. Particularly, only 3 certificate authorities, DigiCert, Let's Encrypt, and Sectigo, serve 60% of the HTTPS supporting websites out of the total 59 certificate authorities we observed. To summarize, our main findings were that third-party critical dependencies are highly prevalent and third-party services are very concentrated. A direct implication of this is that 89% of the websites are vulnerable to DYNE-like incidents. A single provider can affect as much as 25% of the top 100,000 websites. Now the question is, if this is the complete picture, or do we need to take indirect dependencies into account as well? And this brings us to our second question, which is, are there any indirect dependencies between websites and their third-party providers? To do this, we first need to analyze inter-service dependencies between DNS, CDN, and CA providers. In case of CA to DNS dependency, we found that out of the 59 CAs that we observed, 48% of them use a third-party DNS provider. In case of CA to CDN dependency, 36% used a third-party CDN provider. Moreover, out of the 86 CDNs that we observed, we found that 36% use a third-party DNS provider. Hence, third-party dependencies are also prevalent among service providers. In case of critical dependencies, we found that 31% of certificate authorities relied on a single third-party DNS provider, 36% relied on a third-party CDN provider, and 17% CDNs relied on a single third-party DNS provider. These critical dependencies between service providers give rise to indirect dependency. But why should we care about indirect dependencies? I mean, okay, sure, they exist, but what's the harm? Turns out that as a result of indirect dependencies, we see huge amplification in the impact of a given provider. For example, in case of CA to DNS dependency, Cloudflare now critically serves 37% of the top 100,000 websites as compared to 24% before. And in case of DNS made easy, the impact goes from 1% to 23%. Hence, because of these indirect dependencies, we see amplification of provider concentration. To summarize, critical dependencies are also widespread among service providers, and these dependencies can amplify the concentration of service providers, which means that the effect of single points of failures in the internet is amplified, and a single provider can now impact 37% of the top 100,000 websites. this is what we observed for our data in 2020. Now we see how the world changed after the DYNE incident by comparing 2016 dependency data with 2020 data, which brings us to our third question, which is, how did the world change after the DYNE incident? Did websites try to reduce their third-party dependency on service providers? Did the concentration among providers decrease? We observed that critical dependency in DNS increased. With respect to CDN and CA, we see no significant change in the critical dependency. Similarly, in case of inter-service dependencies, we observe an 8% decrease in critical dependency in CA to DNS dependency and a 4% decrease in CDN to DNS dependency. So overall, in terms of provider to DNS dependency, we see a decreasing trend, which is encouraging. Now let us look at the change in concentration of service providers. According to this figure, in 2016, 2,700 DNS providers served 80% of the websites, while in 2020, only 54 providers serve 80% of the websites. This means that we are in general moving towards more concentration. This is not an encouraging result because it means that single points of failure actually got bigger. And we see similar trends in CA providers while concentration decreased in CDNs. To summarize, we see no significant change in the third-party dependency trends among websites. We do observe a decline in third-party dependency among service providers. We also observed that services became more concentrated in 2020 as compared to 2016. All in all, we do not see an increasing trend in redundancy. We did observe that websites using DYNE were more redundantly provisioned in 2020 as compared to 2016. But in general, there was no significant trend towards redundancy. And because the concentration of providers increased in 2020, single points of failure actually got bigger. Now, based on these findings, we make some recommendations. For websites, they should consider redundancy while using a third-party provider. Moreover, they should try to understand their indirect dependency arising from the inter-service dependencies of the providers that they're using. Similarly, for service providers, they should make it easy for websites to be redundantly provisioned. As we observed that many DNS providers do not support redundancy. And also, service providers should try for redundancy in their inter-service dependencies. Finally, service providers should also try to be more transparent about attacks on their infrastructure. To highlight some of the limitations of our work, our measurements are from a single vantage point only, and hence we may miss region-specific dependencies. We analyze dependencies only on the landing page of a website, hence we may miss dependencies that manifest deeper in the content hierarchy. A direct consequence of this could be that we may miss certain CDNs used by a website because their landing page didn't access any resource from a CDN. Finally, we also did not look at the physical and networking infrastructure dependencies such as routing and hosting, mainly because it's not the scope of this work. To summarize, the DDoS attack on DYNE in 2016 raised some questions about the resilience of the internet. In our paper, we try to answer some of these questions, particularly about the prevalence of third-party dependencies and their impact. To do so, we analyze top 100,000 popular websites. We also look at their inter-service dependencies to get a holistic view. And we identify the potential single points of failure in the internet. We see that third-party dependencies are highly prevalent. Indirect dependencies amplify provider concentration, and we do not see a move away from third-party dependency after DYNE incident. The code and data used in this paper is actually also available online. Thank you so much.
Okay, thank you, AXA, for that really interesting talk. Please do come on up. Hi, can you all hear us?
Can you guys hear me?
Yes, we can. Yes, we can. All right. So yeah, as I say, thank you for the really interesting talk. We had a bunch of really good questions in the chat already, and I see a couple of people in the queue. Wes, I guess you're first.
Hi. Yeah, thanks a lot for the work. Measuring.
I'm not able to understand. I think my internet maybe is very bad.
Uh-oh. Can you hear me? Or anyone?
I'm sorry for this. I'm not sure why this is happening.
I can hear you, Wes.
Yeah, I think it's her reception it's odd. Her transmission looks great. Her picture's great. So. Give her a minute, I guess.
Yeah, you heard connection drops out.
Yeah. You might have to take her questions after the other presentation or something.
I think I can hear now. If you.
Oh, good.
Yeah.
Okay.
Can you hear me?
Yeah.
Okay, great. So thanks a lot for the work. So it's, any studies we get on centralization and dependencies is fantastic because it's definitely a trend, as you have proved in your numbers. You made one statement that said, so in your recommendations, you said that you recommend that companies be more transparent. Is there any data to back that up, or why companies should be more transparent? That has been something that people want, but it's hard to prove that that's actually a good thing for them to do.
So actually, I have a multiple sort of data points for this. For instance, currently, let's say I'm doing research in the DDoS area, and when I say that companies should be more transparent, what I mean is that they should be transparent about what attacks they're observing so that we can sort of determine the skill level of the attackers to some extent. For instance, here in this attack that happened, we don't really know for the Dyn attack, we don't really know if the target of this attack was particularly Dyn, or if the target of this attack was some other website and all other websites were just collateral damage. And these kind of questions can actually help in making informed decisions, because if many websites just became collateral damage, then people might want to think about, okay, also having a private provider rather than just having third-party providers. And if a particular provider was specifically being attached, then we can make an argument that, okay, maybe we should be redundantly provisioned. And not in just this attack, but there are many other attacks. For example, currently I'm working on building attackers who can do reconnaissance on different service providers. And these type of attacks have existed for so long. I look at all these companies, Akamai, Verizon, and their DDoS reports, and I see that they talk about, okay, these attacks have existed, but we don't really know. We don't know how to detect these type of attacks, how the attackers were actually doing this attack. And I think this is very important for at least research in DDoS attacks to know that what the capabilities of existing attackers are.
That makes sense. Thank you.
Okay, thank you. Elliot, I guess you're next.
Thank you again, Colin. Aksa, this is a great paper. I echo what Wes said. It's a really helpful in an area that is, I think, really challenging, given our dependency on the internet today. 2 points. First, the numbers you presented in terms of concentration very much are consistent with the numbers that Anna Maria Mondolari at Imperial College showed when she was looking at IoT cloud dependencies. So you can look up her work if you'd like. I think she presented at IMC as well at some point about this. The second point was just that there's an activity going on inside the IETF which may benefit from hearing more about your work, which is Benoit Clay's presented something called SANE. Please don't ask me to expand the acronym, I couldn't possibly. But it essentially is a dependency, it's a service architecture and looks at and it's based on a dependency graph. And there's a lot of work actually going on in the ops and M area that is focusing on this very important area of resiliency. So again, congratulations on a great paper. And I look forward to seeing a lot more interesting stuff from you and your colleagues. Thank you.
Thank you.
Yeah, thank you, Elliot. If you could put a pointer to Benoit's stuff in the chat, that might be helpful. All right. Other than that, I notice we're running short on time. We've had a bunch of really interesting questions there. Please do reach out to AXO if you have more questions. And so, as everyone has said, this has been a really nice piece of work. All right, and with that, we should move on to the final talk today, which is by Kevin Bock. Kevin is a PhD candidate in the Department of Computer Science at the University of Maryland, advised by Dave Levin, and his work focuses on enabling open communication, improving network security, and evading censorship. And if we can have the final video, please.
Hey everyone, my name is Kevin Bock from the University of Maryland. Before I get started, I wanted to give a huge shout out to all the IETF organizers for making this event possible, doing all this remote organization. And I wanted to give a big thank you to all the collaborators on this project. It's really taken a village to get this going. Now I'm going to be talking about censorship today, and specifically a new form of censorship evasion we've been working on, server-side evasion. Before I get into that, though, I wanted to give you all a brief background of what nation-state censorship looks like nowadays to motivate some of the approaches we've taken. Now, there are many types of censorship that operate around the world today. And today, I'm going to be talking specifically about the automated in-network censorship that operates in the network by nation-states. Now, some nation-states operate censorship as in-path sensors, like this one, with the sensor physically sitting inside the network path. Other sensors operate censorship like this. Instead of being in the path, they're on the path. So if the client makes a forbidden request, you can see this request moving through the network. Now the server will get the packet, and the sensor will too. If the sensor wants to censor this connection, though, it can't drop it anymore because it's no longer in the path. So instead, it performs deep packet inspection on this packet. And if the packet contains something it disallows, what it will do is it will inject its own packets into the connection. Specifically, it will inject spoofed TCP reset or teardown packets. These are normal packets our computers send all the time. These just exist to tell the other side, stop talking to me immediately. It's going to send one of these packets to the client, pretending to be the server, and one of these packets to the server, pretending to be the client. And when these packets arrive, the client thinks the server terminated the connection, and the server thinks the client terminated the connection. Immediately, both of these sides stop talking to each other, and just like that, censorship has been achieved. Now, in order to pull off this attack of injecting teardown packets, the sensor needs to have some information about the connection. It needs to know the port numbers, the sequence of acknowledgement numbers. What this means is that the sensor requires per flow state. And that means that these sensors have to be tracking the full state of every TCP connection coming into and out of their country. And if you're trying to track every single connection into and out of a country, at a country the scale of something like China, you're going to necessarily have to start taking some shortcuts. And we as evaders can take advantage of some of those shortcuts. So let me give you an example from prior work of how researchers were able to take advantage of these ideas to evade censorship. Now, once again, our client is about to generate a forbidden request to this resource. But this time, we're going to inject a TCP reset packet of our own. We're going to set it in such a way that the TTL, or time to live, this is a field in these packets that tell the network how long it should survive in the network, and it decrements once per hop. We're going to set the TTL high enough such that we reach the sensor, but not so high that we reach the server. So watch what happens when we send this packet. Now, just like before, the sensor will get a copy of the packet, but the packet's not going to reach the server. It's going to get dropped along the way. Now, the server never saw this packet, but the sensor has. And the sensor says, well, it looks like the client just terminated this connection, so I can stop tracking the connection now. And it throws away the state it's been maintaining about the connection. Now, for the rest of this flow, the client and server are free to communicate. The sensor has no state with which to censor us, and the server has no idea we pulled off this trick. Now, this is just one example of these strategies that have been developed and discovered over the last 10+ years. And the one thing they all have in common is that evasion has always involved the client. And that statement is true even beyond ways and mechanisms of evading censorship that do not rely on manipulating your packet stream. Consider Tor or VPNs or proxies. All of these things require the client to install some software on their system or take some direct action to make them happen. This has always posed a significant barrier to deployment, though. Installing the software can pose significant risk to the user in the first place. And beyond that, it can help users who either don't have the technical know-how to set these tools up, aren't comfortable doing so, or even those users who don't even know they are experiencing censorship in the first place. Now, ideally, servers would be able to help. Instead of deploying software at the client, instead, we would deploy it at the server. And if such a thing were possible, then the server could subvert censorship on the user's behalf without clients needing to deploy anything at all. And just think about the benefits of this. This would immediately broaden reachability and accessibility for these resources without clients needing to do anything. Many clients connect to one server. Clients no longer need any technical expertise or to download anything. Every client immediately gets plausible deniability. And it helps all those users who don't have technical expertise or don't know they're being censored in the first place. So this sounds amazing. The problem is it shouldn't work, and it shouldn't be possible. And to see why this is, let's consider the waterfall diagram of packets that are exchanged leading up to some censored query. Client's going to send a SYN, to which the server responds with a SYN-ACK. The client completes it through a handshake, and then the censored keyword is sent. From the server's perspective, though, there's very little it can do before the censored keyword is sent. In fact, the server can't influence this connection past the SYN-ACK at all. Underscoring the difficulty in this space, there's been no prior work on evading censorship from the server. Now, I'm thrilled to tell you that server-side evasion is indeed possible. And in the rest of this talk, I'm going to talk about how we discovered these server-side techniques and our results across multiple different countries and protocols. And then I'm going to talk about the insights we glean from the sensors in these experiments. Before I jump into discovering server-side evasion techniques, I wanted to first give you a little bit of background on the tool we used and modified to discover these strategies and get some insight into this idea. Now, this tool is Geneva. Geneva is an open source, originally client-side tool that my team built a few years ago for automatically discovering censorship evasion strategies. This was originally published by my team in 2019. Geneva runs strictly a one-sided connection. We originally designed it for the client side. And the way it works is it manipulates packets as they enter and leave the system. Now, Geneva is a genetic algorithm. So in fact, it learns how it should manipulate packets. Specifically, the way it can manipulate packets is it can do that with just 4 actions. That's duplicate, you take one packet, you have 2 packets. Tamper, you take a packet and you change it in some way. Fragment, take a packet and break it in half. Or drop, you take a packet, you drop it on the floor. Now, I'll call out 2 things specifically here. The first is that tamper is allowed to alter or corrupt any TCP/IP header fields. Importantly, we don't give it any semantic understanding of what these fields mean. We give it syntax, but not semantics. What this means is that it can access the TCP flags field. It can change the flags fields, but it has no knowledge that if I set the flags field to SYN, that means the start of a connection. So syntax, no semantics. I'll also call out fragment here. It does a bit of double duty. The IP layer does fragmentation, but it can also do segmentation of the TCP layer. Now let me show you what it looks like when Geneva puts these actions together. Because Geneva actually composes these things into trees. And these trees look something like this. At the top, we have some sort of match or trigger. Okay, and then associated with that match, we have an action. These are match action pairs. And a strategy is comprised of some combination of these match action pairs. So for this specific strategy, the trigger is outbound TCP packets where the flags is set to ACK. Okay. When that match happens, when a packet matches that trigger, it gets pulled into the tree, and then the tree decides how that packet should be modified. The duplicate action makes 2 copies, and then you can see different things happen to each copy. Then we do an in-order traversal of the leaves, and we send the packets that emerge. So let me show you what this looks like on the wire. Once again, our client has just finished the three-way handshake, or they're about to finish the three-way handshake, and they're about to make a request to this forbidden resource. We're going to generate our ACK packet, which matches the trigger. Geneva pulls it into the tree, duplicates the packet. The left child is done. The right child, the flags are changed to reset. The TTL is changed to 2. And then in-order traversal of the leaves, and we send the packets. And if you'll notice, this tree exactly implements the censorship evasion strategy that I opened this talk with. This is the TTL limited reset. Now for this work specifically, we modified Geneva so that it could run on the server side. Then we deployed it against real-world sensors. In our previous work, and a lot of other previous work in this space, we've tended to focus on HTTP. In this work, we've broadened the protocols that we try and subvert censorship for. So specifically, we look for HTTP, HTTPS, DNS, FTP, and also SMTP censorship. Now, triggering censorship for these protocols largely involves making requests or queries with forbidden keywords and domains. SMTP is a bit of a special case. For SMTP, you can just send an email to this email address. This is censored in China, and for context, this email address is an old mechanism by which how bridge nodes used to be distributed in China. So the email is censored. To show how this could be applied broadly, in addition to the diversity of protocols, we also tested against a diversity of sensors in both how these sensors operate and where they're located. So we tested in China, Iran, Kazakhstan, and India across all of these different protocols. Now, I do want to note there's a small asterisk on the slide. This refers to that although Iran censors DNS over UDP, at the time of our testing, DNS over TCP was not censored from any of our vantage points. Now, recall that server-side evasion shouldn't be possible in any of these cases because the server can't really influence the connection past the SYN ACK. But Geneva was able to find ways to do it, and I would love to show you what some of those things look like. So this is one successful server-side evasion strategy that works in China. Now, there's a lot going on here, so let me break this down. The client starts off just like normal by sending a SYN packet, okay? Now, instead of the server responding with a SYN ACK, it doesn't respond with the SYN ACK anymore. Instead, it responds with 2 SYN packets. The first is a normal SYN packet. The second is a SYN packet containing a payload. Now, this amazingly is legal. The first SYN packet serves to trigger a TCP simultaneous open. This is an archaic feature of TCP that's still supported by every major platform. And this was originally written to handle the case of what happens if 2 computers send a SYN packet to each other at the exact same time. Now, when the client receives the SYN packet, the client now sends a SYN ACK. And it's actually this combination of the client sending a SYN ACK, immediately preceded by a SYN packet containing a payload that causes the Great Firewall of China to desynchronize from the connection. And for the rest of this flow, the client and server can now communicate censorship-free. Now, this seems crazy, but this actually works with varying degrees of success across all the protocols we tested. And for context, the baseline success rate, if you do nothing at all, for evading censorship is about 2%. Now, this is one successful strategy, but it's actually just one of many. Altogether, we found 11 different strategies at the time we did this work. We discovered 8 in China, 1 in Iran and India, and another 3 in Kazakhstan. Now, our paper goes into detail across all of these, and unfortunately, as much as I would love to, I don't have time to go through them all now, but I would love to show you just 1 or 2 more. The next one I want to talk about takes place in Kazakhstan. This is the null TCP flags server-side evasion strategy. You'll notice it starts off just like all of them do. The client sends a SYN. But the server, instead of responding with the SYN ACK, instead what it responds with is a packet with no flags at all. Now, the client, when it sees a packet with no flags, it has no idea what to do with it, so it just drops it and ignores it. But when the sensor sees a packet with no TCP flag set at all, the sensor can't handle it and assumes there's something wrong with the connection and immediately stops tracking the connection. And just like that, the server has helped uncensor the client. Now, one of the big takeaways from this is that it really has helped motivate why we should be using automated techniques to discover this. This is likely a bug in this sensor that it may have been difficult for a human to discover. Now, here's another example that I wanted to show you, also in Kazakhstan. Now, in this one, during the three-way handshake, instead of the server sending one SYNAC, it actually sends two SYNACs, and it includes payloads on those SYNACs. Specifically, the payloads it includes are two uncensored GET requests for something like example.com or something innocuous. And of course, the client is just going to ignore these payloads. But when the sensor sees these well-formed HTTP GET requests on these SYNACs, the sensor confuses the connection direction. It says, whoa, the server is sending this data. I must have had this mixed up. The server must actually be the client. And it reverses the roles of client and server in the mind of the sensor. As a consequence of this, because it treats packets differently from the client and server, when they begin communicating again, and when the client issues the real censored query, they can now communicate scot-free, because the sensor is no longer examining the packets from the client the way they should be. And this works with a 100% success rate in Kazakhstan. Now, at this point, we've seen a lot of different types of bugs in sensors, not handling esoteric features in TCP correctly, error cases, or just confusing the logic altogether. For more details for any of these, I'll refer you to the paper, but I will note that all of these do not require any client behavior whatsoever. They may induce some behavior from the client, but no software changes is needed. And we tested this across a wide range of diverse clients. And in fact, we found only one case of a strategy that relied on platform-dependent behavior. We were able to very quickly rewrite that strategy to make it platform agnostic. And all of these really teach us more about how sensors work. Next, I'd like to talk a little bit more about the insights this work has helped provide us with. So the first thing I'm going to talk about is something called the resynchronization state. This is a feature of the Great Firewall of China that allows it to be more tolerant to packet loss. So specifically the way this works is, let's say the sensor misses a packet. The idea is simple. It can just resynchronize its state on a later packet in the connection. Now, the exact dynamics of the resynchronization state are constantly evolving over time, and understanding how the resynchronization state operates allows us to build better censorship evasion tools. So looking at the resynchronization state gives us some more insight as to why that first strategy I showed you actually works. So once again, here's that strategy. And I'm going to focus right now on the second SYN packet we sent from the server. If you recall, we sent this SYN packet, again, we sent it from the server, but we sent this SYN packet including a random payload. We notice here is that this payload actually triggers the Great Firewall's resynchronization state. It tells the Great Firewall, hey, you may have missed something. Go resynchronize on the next packet. The next packet that it resynchronizes on is the SYNAC packet from the client. But because we force a TCP simultaneous open, when you do a TCP simultaneous open, the mechanism by which sequence numbers are incremented during the three-way handshake changes. And the Great Firewall is not properly incrementing its initial sequence number while it's resynchronizing. What this effectively means is that this is an off-by-one bug in the Great Firewall of China. The sensor is not properly incrementing its ISN, making it desynchronized from the rest of the connection because of the presence of this payload. Now, strangely, the success rate of this varies greatly by protocol. And in fact, we found that the Great Firewall itself has a different resynchronization state depending on the protocol itself, which is strange. And this is just the first example of protocol variability we found in the Great Firewall. And I'm going to talk about that a little bit more next. Now, all of our server-side strategies operate strictly during the three-way handshake, okay? Which means they happen before there's any application layer specific data going on. What we realized, though, when we started looking at the success rates of these strategies is that they didn't always work the same way with the same degree of success. And this led us to raise the question, why are different applications affected differently in China if the only actions a server takes are done before there is any application layer data exchanged? What this has led us to think about is a new model of how the Great Firewall of China works. Because in the past, we've kind of tacitly assumed that the Great Firewall works with this kind of very sane network model, where it sanely separates application layer from transport layer protocols. It looks something like this. But what's going on here is that we're finding different TCP layer bugs for each protocol, which means that each protocol censorship must have its own TCP/IP stack. And this strongly suggests that the Great Firewall is actually running multiple censoring middle boxes in parallel. It's not just one set of machines. So let's see what this looks like. Instead of just one monolithic sensor, instead we think there are multiple censoring middle boxes, and each of these are running in parallel. Now, this begs the question, how does the Great Firewall know which middle box to apply to a connection? Now, you may look at this and be like, well, it's obvious. It's just got to be using the port number. But it's actually not relying on port number. The Great Firewall for all these protocols can censor effectively on any port. If you try and make an HTTP request for some forbidden content on 80 or 8000 or a random port, it will still censor you the same. So it's not using port number. What we think is going on is that, how does it know which middle box to apply? We think it doesn't. And we think that every single middle box gets a copy of every packet independently. And then every middle box applies protocol fingerprinting. Every middle box checks, hey, is this something I can censor? Does this belong to me? Does this belong to me? And then if it discovers, hey, this is something I should be taking action against, then that specific middle box will take action. Now, this raises the question, where are these guys located? Are they nearby? Are they far away? So what we did was we used TTL limited probes. We sent forbidden queries with for different protocols with different TTL limits. And we tried to see, are these located in the same spot in the network, or are they located far away? What we find is that largely they're co-located at the network level. They don't seem to be located at different locations. Now next, I want to shift gears a little bit, and I want to talk about where we've taken these ideas since we wrote this paper. Now the first thing I want to talk about is how this idea of server-side evasion and this idea of an automated approach to server-side evasion has allowed us to be highly responsive to new forms of censorship. Back in February of 2020, Iran launched a new form of censorship called a protocol filter. The way this works was that it monitored all protocols entering and exiting the country on certain ports, and it only allowed certain of those protocols to happen. It performed protocol fingerprinting across all of these, and protocols that didn't match were then subject to censorship, which means if you tried to use a protocol they didn't approve of, regardless of if what you were doing was innocuous, they would take that connection down. In fact, the only connections they did allow were those that were able to be filtered by their standard censorship system. So within a small amount of time of this censorship system being deployed, we threw Geneva at this problem, and we were able to discover 4 strategies to evade this filter, 4 from the server side. So this means that as soon as Iran rolled this out, we were able to defeat this thing and help roll out those evasion tactics to those in Iran. Another example of new censorship events that occurred is last summer, China began censoring the use of encrypted SNI. This is a new feature in newer versions of TLS, whereby the SNI, or server name indication fields inside TLS, is encrypted. Now, the SNI field is a field in TLS 1.2, where when a client connects to a server, the client announces in plain text the domain it's trying to get to. SNI is clearly a privacy leak, and the TLS developers are working on fixing that. But SNI is how censors have been censoring HTTPS for quite some time. ESNI, people have been looking forward to as a mechanism by which they could protect themselves from SNI-based censorship. And unfortunately, last summer, China decided to ban the use of ESNI completely. So if you try and encrypt your SNI field in any connections, China will take action against that connection, even if you're talking to something innocuous, and has effectively stopped the rollout of ESNI within the country. Now, within 24 hours of China rolling out this system, Geneva had discovered 6 strategies to evade it, 6 from the client and 4 from the server. So this is very exciting, and it really allows us to be highly responsive and dynamic as new censorship events occur. Now, the other exciting direction we've been able to explore since this work has been a real-world deployment of this system. And we've been working with a number of anti-censorship groups to integrate our software and our findings into their systems. And we're starting to see success with this. We've been using Geneva to help really in 2 regards. The first is in bootstrapping initial connections. So let's say you're something like a VPN, and you really want to help users get connected initially. And the weak spot in a lot of these protocols is that initial connection, is those API calls, that initial reaching out. Now what we can do is use Geneva to help protect those initial bootstrapping and assist in bootstrapping clients from a weaker protocol to a more secure protocol. The second thing we've been able to help with is in hardening existing evasion protocols. Evasion protocols that censors may be working on harassing or taking action against. Use Geneva on top of those and deploy these server-side strategies to protect those in use and make it harder for censors to take action against these. And we're very excited about these new directions. I want to conclude here to talk about new directions that this work has opened up for us, and really how it's changed the way we conceptualize middle boxes, because these middle boxes are really creating new possibilities in the network. It's good because this has opened up the ability to do censorship evasion to more people, even those who don't know they're being censored. Now, this is made possible, though, by the ugly fact that middle boxes have bugs and bad assumptions that can be exploited. And unfortunately, this can also lead to some very bad directions. In another recent piece of work, we showed that middle boxes can be actually weaponized by attackers to launch attacks that were long thought impossible. Ultimately, this leads us to conclude that to really make sense about what these new additions to the internet are doing, we really need to keep investing in automated tools like Geneva to understand what new things these middle boxes enable and how they change the landscape of the network and networking research. Now, I'm going to wrap up here. Today, I've talked about Geneva and specifically how we've applied it to make server-side evasion possible. If you want to learn more, our website is available here at the slide. It's geneva.cs.umd.edu. Thank you all very much.
All right, thank you, Kevin. Really nice talk. Are you there? Yes, hi. So I see a tremendous amount of discussion in the chat already. Are there any questions which people haven't asked already in the chat? I see Spencer maybe. What else do we have? Stuart, yes. Please join the queue if you have questions. All right, Wes, go ahead.
Well, since you needed questions, and then two more people popped up. So it was unclear to me, and maybe I missed it. How did you determine ground truth for, if you were doing server-side, studies, how do you decide whether something is successful or not and actually got transferred to and from the client properly?
Can you hear me? Let me know if my audio is not great. So in our case, we had the good fortune of being able to control both the client and the server. So we did our experiments. We actually had vantage points located in all of these censored countries, and so ground truth was very easy to determine. We could try and obtain some forbidden resource, see the censor take action, and then try and do that again with the server-side strategy running and see it succeed. Now, when you're talking about scaling this up to cases in which you don't control the client, or some of our more real-world deployments that we've been working on recently, that starts getting a little trickier. And you start needing to really look at telemetry and look very carefully at if the packets are getting exchanged, if the connection is staying alive, that sort of thing. I will say most sensors, when they take action against the connection, it's fairly obvious. Like they're usually not quiet about it. So generally, the server can determine pretty accurately whether a sensor is taking action against something or not.
Okay, thank you. Shiva?
Hey, Kevin, thanks for the talk. Can you hear me okay? I think you might have touched upon this, but when it comes to deploying this at scale, I think you mentioned like TunnelBear, someone you were working with, but just wondering, were you thinking about coming up with the strategies in a centralized way and then distributing those strategies to every server running Geneva, or were you thinking that every individual server deployment would come up with its own strategies? What were you, thinking about coming up with the strategies themselves from a deployment point of view?
For initial rollout, the methodology has been will be kind of a strategy oracle and provide strategies. I didn't get to talk about it too much in the talk, but Geneva is broadly broken into two halves. There's the component that runs the strategy on the network, and a genetic algorithm that discovers the strategies, and those are fairly self-contained. So for now, we've had success with having third parties deploy the strategy engine, the thing that takes the strategy and runs it on the network. And we've been more a strategy oracle providing strategies. That being said, there are more and more groups who are working to find strategies themselves. And so as that becomes more decentralized, things will just continue to improve.
Okay, great, Maria.
Yeah, and thanks a lot for this talk. It was very interesting to learn what the sensors are doing there, and I probably have to read the rest of the paper as well to understand what's happening there. We talked a little bit in the chat about this is a cat and mouse game, right? Can you just tell a little bit about like how long, because I think somebody said in the chat that some of these bugs have been fixed. So like what's the timeline? How long did it take? What was the dynamics behind that? Just curious.
Yes, that's a really great question, and that's something we're still studying of what does it look like when a nation state rolls out a bug fix? Like how long does that take? Where does that go? That's still something we're studying, and I don't think I have a great answer for you. I think I'll put a TBD. Stay tuned on that. It's something that's super interesting, and we're going to keep monitoring. And we do test these things fairly often to see what goes on. But I don't think we have a great understanding yet of how those fixes get rolled out. And part of that is a limitation of that can be quite difficult to do at scale. For example, a country like China may have many instances of middle boxes, and I mean, perhaps a fix gets rolled out somewhere and it takes time to traverse, or there's different sets of middle boxes doing things. So it really takes quite a concerted effort to measure these things at scale and get a good understanding of how the fixes move through the network, if you will. So a big TBD on that, but it is a super interesting question.
Okay, thank you. I will read your next paper, but yeah, it's already known that the system is very heterogeneous, so it's probably hard to measure. Great.
All right, Andrew, I think is next. Siobhan, are you supposed to still be in the queue?
Yeah, shall I go ahead? Yeah. Yeah, hi Kevin, thanks. Very interesting presentation. Just to amplify a comment I made in the chat, which you answered, but I think clearly I can see nation states have the resources to respond over time with countermeasures, etc. So it's an arms race and no side will win, I think, by definition. Possibly China might, because they've got more resources than anybody else, but notwithstanding that, my concern is for the non-nation states affected by this. So if you like, for the typical end user versus the malicious content developer. Clearly server-side evasions in the hands of malware has seriously bad implications for most end users. If you like, any tool can be used for good and bad. I think this tool has tremendously negative connotations for the vast majority of internet users, which doesn't negate the work, but I think that needs very, very careful consideration.
True. I mean, it's a true statement generally that anything like this can be used for good and bad, and malicious. I think Dave said it best. Malicious is in the eye of the beholder. So we've intentionally not taken this work and applied it towards the firewalls like you're describing. Like this really has been a very concertedly focused effort on nation states to try and at least angle things towards the good side as we can help direct it. I think it's difficult to quantify if who's affected in the majority here. I mean, there are billions of people living under censored regimes. There's also billions of people who would like to be protected by firewalls. So it's kind of a tough question to answer, but it is something we've been thinking about, and it was a serious consideration. We were talking about, should we release this tool? Should we make it open source? At the end of the day, we thought it best to put it out there and let the community use it.
I guess I would observe that some of the earliest adopters of, for example, encrypted DNS were malware. developers. So malicious content in the way that in a definition that most of us would recognize as malicious. Yeah. Anyway, food for thought. Certainly. Thank you.
Yeah, it's a difficult problem. I'm tempted to say the only winning move is not to play. Just following on a little bit from that, can you say, I think you've touched on this to some extent already, can you say something about how you did the tests and how you protected the users who are running the tests in these countries?
So in these cases, ooh, we got some bad echo here. Is this on me? Are we good? Okay, we're good. In these cases, we did all these tests ourselves. So there were no end users directly involved in no end users were harmed in the making of this paper, if you will, and no end users we tried very hard to not put any end users at risk. It was from machines directly at our control, and we monitored all that very carefully. Going forward, as these things are deployed, that's a whole separate question, and that's something that as people deploy these things, they'll have to wrestle with those. But at least in all the work we did and in those circumstances, there were no users involved.
All right, great. Thank you very much. We are basically out of time here. I think we've had 3 really interesting talks. We've had a bunch of really interesting discussion. If anyone here would like to follow up with the rest of the authors, please do reach out to them. I'm sure everyone involved will be happy to chat more. People may be around for the rest of the meeting. We have the gather space if people want to chat afterwards as well, which is all linked from the agenda. Really nice talks. As I say, please reach out to the authors, and please submit your nominations for the prize for 2022. And the deadline is, I believe, the end of next week. So thank you, everybody. Thank you again, and that's all we have. So thanks, everyone.
Thanks, Colin.